Good morning, class. We are looking at exam to review, chapter 3, differentiation rules. Exam 2 covers 3.1 to 3.8, and here's part 2 covering 3.4 and 3.5. 3.4, the chain rule, 3.5, implicit differentiation. So how would you differentiate composite functions? Example, y equals square root of 10x plus 5, fx equals 10x squared minus 1 to the power of 50. We use the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function f of g of x is differentiable at x. d dx of f of g of x is f prime of g of x times g prime of x. Please understand, f is the shell function, is the main function, the outer function, and g is the inner function. So you differentiate the outer function, the shell function, f prime of g of x, and then multiply by the derivative of the inner function, g prime of x. Or in Leibniz notation, if y is a function of u, so that's f of u, and u is a function of x, that means u is g of x, dy dx is dy du times du dx. To recap, if capital F of x represents f of g of x or f of g of x, to differentiate this, d dx of f of g of x, we would differentiate the outer function, the shell function, f prime of g of x, and then by the chain rule, we multiply by the derivative of the inside, g prime of x. For the extended power rule, you recall that the basic power rule says d dx of x to the power of n is n x to the power of n minus 1. But instead of x, if we are dealing with g of x, so following this format, n, the exponent becomes the coefficient, x to the power of n changes to x to the power of n minus 1. So g of x to the power of n changes to g of x to the power of n minus 1 because we subtract 1 from the exponent. For this one, we don't write anything because what is the derivative of x? If we wrote that, it would be 1, but the derivative of g of x is g prime, and we need that. That is the concept of a chain rule. So one way to understand the chain rule is to look at the following trigonometric functions, all of them involving sine. And in order for you to differentiate them, I'm going to show you the method that I use. When I come across sinusoidal functions or any trigonometric functions, the way I read is this: y equals a sine, and I pause. The derivative is cosine. However, every trigonometric function must have an argument, and the argument here is 2x. So I have to use the same argument. If it's x, I'm done, but it's a function of x by the chain rule, I need the derivative of that. So times 2, and I put the 2 in front. Same thing here. I'm going to read sine, and I'm going to stop, and the answer is cosine. The argument is x squared. I need the same argument. If the argument is x, the derivative is 1, and I'm done, but it's not. By the chain rule, I need its derivative, which is 2x, and I must put it in front. The last one, if you recognize that is sine of x to the power of 2, that will do the job. You don't have to rewrite it in this format if you recognize it. So 2, so you're dealing with the extended power rule. 2 becomes the coefficient, the same thing to the power of 1, and then the derivative of sine, which is cosine. So 2 sine x, cosine x. Let's move on and take a look at this example where y is u to the power of 5 or a function of u, and u is 10x cubed plus 2 or a function of x. And we are going to do this two ways. We're going to start with the Leibniz's notation. dy dx is dy du dx. And notice, by the way, if you think of them as a fraction, these two cancel each other, but that's not the case. They are not fraction, okay? So dy dx is dy du times du dx. So if you look at this piece, dy du means take the derivative of this function with respect to u, because u is the independent variable. So it's a simple case of a power rule. So 5 u to the power of 4. Now du dx, 10x cubed gives you 30x squared, and a constant gives you 0. And you're done. All you have to do, replace the u with 10x cubed plus 2. And then we have the 30x squared. The product of these two sits in front, 150x squared times the parentheses 10x cubed plus 2 to the power of 4. This is simple enough. We can find the composite function y equals f of g or f of g of x. So what is y equal to? Replace the u with the g function, which is 10x cubed plus 2. So this is 10x cubed plus 2 to the 5th power. So we find the composite function first, and then y prime is f of g prime, f prime of g of x times g prime of x. So something to the power of 5, that is the shell function, the outer function, or the concept of an extended power rule. So 5 sits in front, then the same thing to the power of 5 minus 1, so 10x cubed plus 2 to the power of 4. Finally, the derivative of the inside. This is the idea behind the chain rule. What is the derivative of the inside? What is g prime of x? What is g prime of x, where g of x is 10x cubed plus 2? That is 30x squared. And the product of these two, again, puts 150x squared in front, and it gives you the same expression as up here, 150x squared times 10x cubed plus 2 to the power of 4. I want to differentiate this, and it is important to remember the formulas. So if I'm differentiating this, first of all, this is to the power of 1/2 according to this. Everybody remembers the exponential rule. And then I'll bring it up and make it to the power of negative 1/2 according to the negative exponential rule. Remember, if the exponent is negative, take it down, make it positive. If it's down there and it's negative, bring it up, make it positive. Either way, so we should be able to go from left to right, right to left. This can be represented in this format. Because the numerator is a number, we do not have to use the quotient rule. Instead, we are going to use the extended power rule. Now, the way I am going to do that is that I will write the formula for me. I would write this formula. This is a shorthand notation. d dx of g of x to the power of n is n g of x to the power of n minus 1 g prime of x. This is the extended power rule. Instead of writing d dx of this, d dx of that, and it becomes cluttered and not easy to deal with. So I want to differentiate this. Number one, I have the number 4, I'm going to write. Then according to this formula, the extended power rule, n becomes the coefficient, so I put negative 1/2. Then I put the same thing, to the power of n minus 1. So minus 1/2 minus 1 makes it negative 3/2. So subtract 1 from this number. So this is minus 1/2 minus 1. And finally, I need g prime of x, the derivative of the inside, which is 2x, and I'm done with calculus. For a negative 1/2, the product is negative 2 with 2x is negative 4x. I take this down, make it positive 3/2. In other words, minus 4x over x squared plus 3 to the power of 3/2, and I represent it with the square root format because that was given in that format to begin with. Y equals cosine of 3t to the power of 4. The way I'm going to deal with this, I'm going to read cosine and I'm going to pause. Cosine, that's all. And I know the derivative of cosine is negative sine, so I'm going to put negative sine. But every sinusoidal function must have an argument, so it needs the same argument, namely 3t to the power of. By the chain rule, I need the derivative of this one. Let's say if it was x or t, the derivative would be 1. We don't have to worry about that, but it's not. So the derivative of that is 12t cubed. Or you can look at this formula that I wrote for you. Do d dx of cosine of g of x is minus sine g of x. So this is g of t. And then g prime of x. So we need g prime of t, 12t cubed. This sits in front, and we are done. So just follow the formula, and it makes it very nice and easy. We want to differentiate this, and again, we notice if we cut this into two fractions, this results in x. This results in 4, and all we have to do is use the extended power. So 6 sits in front. Then x plus 4 to the power of 5. Then the derivative of the inside happened to be 1. And I write it on purpose because in case we don't have 1, I don't want to make a mistake. So the derivative of x plus 4 is 1. And of course, you rewrite this and you're done. Y is 2x plus 3 over x minus 8 to the power of 5. To differentiate this, we use the extended power rule in conjunction with the quotient rule. In other words, we use the chain rule and quotient rule. According to the extended power rule or the chain rule, 5 sits in front. Then we need g of x, whatever is inside, to the power of n minus 1, this one to the power of 4. And then the derivative of the inside. This is the derivative of the inside, so I'm going to call it f over g and use the quotient rule. Again, if you go with the shorthand notation, so I would write this formula next to me and follow it this way. It's easier to follow. F prime g minus g prime f over g squared. So this, the derivative is 2 times x minus 8 minus g prime f. The derivative of this one is 1 times 2x plus 3. And finally, just write the bottom, put it in a parentheses and square it. So x minus 8 quantity squared. And this is the end of calculus. So let me put the asterisk next to it. So this is done as far as calculus is concerned. Now we use algebraic techniques to finish the job. We're going to distribute. We get 2x minus 16 minus 2x minus 3. These two cancel each other. These two add up to negative 19. So just to avoid any confusion, we are going to rewrite this as 2x plus 3 to the power of 4 over x minus 8 to the power of 4, because in case you don't see how they combine. So 5 remains, this one 2x plus 3 to the power of 4, this one x minus 8 to the power of 4, and this one minus 19 over x minus 8 to the power of 2. This belongs to the numerator. So 5 times negative 19 makes it negative 95. 2x plus 3 to the power of 4. This belongs to the denominator. So x minus 8 to the power of 4 plus 2. And that makes it x minus 8 to the power of 6. And this is the final answer. As you can see, one step of calculus, many steps of algebra. We remember that the derivative of e to the power of x is itself. We also know the composite function, the derivative of f of g of x is f prime of g of x times g prime of x, known as the chain rule. Therefore, if I'm interested in finding the derivative of e to the power of g of x, according to the chain rule, the answer will be the same thing times g prime of x. So the same thing times the derivative of the exponent. So if it's to the power of kx, the derivative of the exponent is k. You can follow the formula. The way I'm going to write it is anytime I see an exponential, I just write the answer as itself. So I'm going to write y is e to the power, y prime is e to the power 5t. And then I look at the exponent. Because the exponent is not t, I need its derivative, which is 5. I put it in front, and I'm done. Because it's an exponential function, the answer is itself. Because the exponent is not x, I need the derivative of that, according to the chain rule. So the derivative of tan x, we know it to be secant squared x. And that's done. This one, the only change I want to make, in case we don't see 2x over 3, it means 2/3 times x. I just want to make sure we see that. Therefore, y prime is the same thing times the derivative of the exponent, which is 2/3. We put it in front. We are done. Y equals 2x squared plus 9x plus 9 over x plus 3. Anytime you're dealing with a polynomial or a fractional format, the very first question is, can I simplify it before I move on? It so happened that we can factor the numerator into x plus 3 times 2x plus 3. 2 is a prime number, so it's easy to see that you need 1 and 2, okay? And then 9, you have to go with 3 and 3, or 1 and 9. Make sure the middle terms, they add up. So this would be, let me just actually do this here, that's good. So this would be 3x, this would be 6x, and they do add up to 9x. So that works. You can drop the x plus 3 from the top and the bottom. And this is the easiest piece to deal with. Y prime is simply 2, and you're done. So it's that simple. You don't have to worry about anything. So we know the derivative of e to the power of x is e to the power of x. The derivative of e to the power of kx is k times e to the power of x. The derivative of e to the power of g of x is g prime of x times e to the power of g of x. But what if the base is not e? For example, y equals 3 to the power of x. We don't know what to do. So let's find out. When the base is something other than e, the process is using logarithmic properties. Recall, ln of e to the power of x is x, e to the power of ln x is x, which means logarithmic functions, exponential functions, or inverse functions. So according to this, e to the power of ln x is x, so I can change the b to e to the power of ln b. So take a look at this one. Using this one, we can write b is e to the power of ln b. So again, x is e to the power of ln x, so b is e to the power of ln b. And I'm going to replace the b with that. Now, what is ln b? ln b is a number. Okay, so e to the power of ln b to the power of x, according to the exponential rules, we can multiply these two because that's the power rule, if you will, e to the power of ln b times x. So what you are dealing with now, in essence, you are here, or you can say here, you're here, or here, right? So this we know how to differentiate. The answer is itself times this number. This is like k, ln b. Now, we know this one is the same as this one, is the same as this one, is the same as this one. So we're going to put this back as b to the power of x times ln b, meaning what? If y is b to the power of x, the answer is itself. When the base is not e, ln b. Notice, if it was e to the power of x and you wanted to do this, would be e to the power of x. Remember, ln e is 1, so that works if you expand it. And so for this one, the answer is itself. Since the base is not e times ln 3, and we just rewrite it, and we're done. Two to the power of 7x. And now, in addition to what we did here, we are going to add the chain rule. Therefore, when we have b to the power of f of x, the answer is itself, because it's an exponential, times ln b, because the base is not e by the logarithmic properties, and then times f prime of x by the chain rule. So the answer is itself. Y prime is 2 to the power of 7x, because it's an exponential format. We need ln b because the base is not e ln 2. Again, I emphasize, if it's e ln, remember, even if you go with this route, ln e is 1. And then we need the derivative of the exponent by the chain rule, resulting in 7. All we have to do, rewrite, and we're done. The reason we put this in a parenthesis is because we don't want it to be 22 to the power of 7x by mistake, okay? So 7 ln 2 is a number. By the way, ln 2 is not missing. When you write 7 times ln 2, it's an exact answer, okay? Application, example 16. Observations show that the length L in millimeters from nose to tail of a Siberian tiger can be estimated by the function L equals 0.25 W to the power of 2.6, where W is the weight of the tiger in kilograms. Furthermore, a young tiger's weight can be estimated in terms of its age, t in days, by the function W equals 3 plus 0.21 t. How long is a tiger when it's 100 days old? First, please understand this part is elementary algebra. So when t is 100, we plug in. 100 has 2 decimals. This has 2 zeros. 0.21 has 2 decimals. They cancel each other. The product is 21. They add up to 24. And the units of weight, kilograms. You put that into the L, use a calculator, you come up with the answer 969.369 millimeters. And everybody remembers that 1 meter is 100 centimeters or 1,000 millimeters. So this is almost 1 meter. Straightforward. Now, this part, at what rate is the length increasing when it's 100 days old? Rate refers to either average or instantaneous. Anytime you have one point in time, that means instantaneous, that means differentiation. So you want the derivative of the length L with respect to time. So you want the LDT. Now, I'm going to show you two different ways. So I'm going to start with the Leibniz's notation. And the way I'm going to start is that I'm going to put the dl here and dt here. If you take a look at this one, dy dt is dy du, du dt. So what is u? The intermediate variable that takes the y to t. So the L dt, from L to t, the intermediate variable is w. So L will take us to w, w will take us to t. This is the intermediate variable, so we need to put dw. I hope it's clear to everybody. Now dl, dw, we want to deal with this first. We are going to differentiate this. 0.25 remains, times 2.6, w to the power of 2.6 minus 1 or 1.6. So again, 0.25, 2.6 becomes the coefficient, and the exponent goes down by 1, times dw dt. Now this one, dw dt, take the derivative of the w with respect to t, is just 0.21. And if you multiply this number, and this number, you get this one. Now, right here, if you want to find the LDT as a function of t, you must replace the w with 3 plus 0.21t. However, if you're just interested in evaluating it when it's 100 days old, when it's 100 days old, we know the weight is 24. We replace the w with 24, put it into a calculator, you come up with the answer. By the way, it's important to know that this formula is an estimate. So is this formula. That's why there's no answer such as exact. How many decimals do you use? Whatever they ask you. And we're done. I want to show you the second method. This is easy enough that I can replace the w with 3 plus 0.21t. In other words, find their composite function and make L a function of t instead of just being the function of w. So L of t is 0.25. I replace the w with 3 plus 0.21t to the power of 2.6. Now I'm going to work on this. As far as part A is concerned, if I replace the t with 100, I get 0.25 times 3 plus 0.21 times 100 to the power of 2.6. This part, as you know, is 24, which was used here. And this will result in the same answer that we got here. But what is the weight? We don't know. Needless to say, they didn't ask. But over here, we calculated the weight as well as the length. Now, we want to find the LDT or L prime of t using the extended power rule. So we need the 0.25, we keep it, times 2.6, times this one to the power of 1.6, and then the derivative of the inside is 0.21. So again, 0.25 remains, 2.6 sits in front and goes down by 1, and remains as 2.6. The exponent, this parenthesis remains, and the exponent goes down by 1.6, and then the derivative of the inside is 0.21. We multiply this one, and this one. And what I want you to notice is this. These two are identical. Over here, if we change the w to the expression that was given, we would have gotten this expression. So L prime of t, or the LDT, is 0.1365 times 3 plus 0.21t to the power of 1.6. And we want it when t is 100. If we replace it, we get exactly the same answer as we got here. So this one uses Leibniz's notation. This one doesn't, but it doesn't make that much of a difference because it's simple enough that we can handle it either way. The amount of glass recycled in a community is G of P equals the square root of 0.5 P squared plus 7 tons, where P is the population in thousands. It is estimated that T years from now, the population of the community will be P of T equals 4.4 plus 0.1 T squared thousands. How many tons of glass are expected to be recycled 4 years from now? T is 4. If you plug in here, it gives you the population. Now, of course, 4 squared is 16 times 0.1 is 1.6. With 4.4 gives you 6,000 people. Anytime we deal with applications, we pay attention to the units, 1,000 people. Now, over here, if you plug in 6, you get 0.5 times 6 squared plus 7. 6 squared is 36. Half of it is 18. With 7 is 25. So this is square root of 25, or 5 tons of glass. Elementary algebra, very simple. Find the rate at which the amount of glass recycled is changing with respect to time 4 years from now. Include units in your answers. Even if they don't mention it, you must. And so we want dg dt, and the reason it's a differentiation because there is one point in time. The amount of glass recycled is changing with respect to time, dg dt, dg dt. And I'm going to write it again the same way as I did in the previous page, and say dy dt is dy du du dt, where u is the intermediate variable. So going from g to t, what's in between? The p variable. So we need the dp here, and we are going to differentiate this piece, and come up with the answer. So first, we are going to change this to a power format so we can differentiate this. So we're going to put the same thing to the power 1/2. Please understand this is the same as this one. And so now I can differentiate this easily. 1/2 sits in front. The same thing to the power of 1/2 minus 1 or negative 1/2 times the derivative of the inside, 0.5 times 2p makes it p. So I'm going to repeat 1/2. Same thing to the power of 1/2 minus 1 makes it negative 1/2. The derivative of the inside, 0.5 times 2p. Let me just write this in case. So this is a 0.5 times 2p. That's how we get that. So this is this part. Now to go to this part, we are going to differentiate this part, which is simply 0.1 times 2t. 0.1 times 2t, or 0.2t. Now, there are two ways to do this. You can simplify this. You can even change the p as 4.4 plus 0.1 t squared, or say, you know what? They just want us to evaluate this when t is 4. What is P? We found P to be 6 when T was 4. P, we found it to be 6, but let's use it. So I'm going to show you an easy way to calculate it this way. Just plug in. But if you want to simplify this further, I also show you that method. So 1/2 0.5, P is replaced with number 6, 7 remains. The power of negative 1/2, P is replaced with number 6, 0.2 times 4. Please understand this part is the same as this part is 25. So this is 25 to the power of negative 1/2, which is 1 over 25 to the power of positive 1/2, or square root of 25. So what you are dealing with is 1/2 times 1/5. This remains. This is 0.8. So we write each and every one of them. And this product is 4.8 divided by 10, or 0.48 tons of glass per year. Please understand, as far as the units are concerned, the change in the amount of glass over the change in amount of time. That's how you write the units. Although right here, if you wanted to simplify it, you could have done this way. 0.2t is in the numerator, 2 is in the denominator, 0.2t and p. 0.2 p and t are at top. This is in the denominator. This goes down, becomes the power of positive 1/2 or a square root. Again, right here, p equals 6, t equals 4, evaluate it, or if need be, even change the p. But understand, if you change the p, it just takes a little bit longer to evaluate it. The second method that I'm not going to do is to find the composite function. So if I replace the p here with 4.4 plus 0.1 t squared. So let's go back to this one. If you change the p to 4.4 plus 0.1 t squared, now you have to differentiate this. I hope you realize using Leibniz's notation and not coming up with the composite function, I believe it's easier to differentiate. If you want to differentiate this, it's doable, absolutely, and I highly recommend you practice it at home. But this takes a tad longer than this. Okay? Otherwise, it's really not a big deal. It is doable. We're going to continue with practicing differentiation, where y is cosine to the power of 10 sine x cubed. And you don't have to rewrite it, but I'm going to rewrite it to make sure everybody can see that this is cosine being raised to the power of 10. Never mind what this is. Cosine to the power of 10. So we need 10 in front. Cosine to the power of 9 of the same thing. So 10 sits in front. Cosine to the power of 9, same argument, times the derivative of the inside. Now, so let me show you what we are using. We are using this one, and we have done this one. We have done this one, and this is left to be done. This is left to be done times the derivative of cosine of a sine x cubed. So we need to differentiate that. Therefore, I'm going to read cosine We know the derivative is negative sine. Negative sine of what? The same argument. And then by the chain rule, the derivative of the inside. Now we need the derivative of sine x cubed. Now, if you want to write now, we're going to tackle the derivative of sine of x cubed, which is cosine sine is cosine x cubed. By the chain rule, x cubed gives us 3x squared. This is as complicated as it gets. If you are following what I did, you're in good shape. And also notice, I put the derivative of cosine is minus sine, and then cosine of u is a function of x, is minus sine u du dx. So I'm going to recap this. Of course, we are going to rewrite this. So first, 10 sits in front, the same thing to the power of 9. So cosine to the power of 9. In fact, if it helps, just write this as u or g of x. So 10 cosine of u to the power of 9. Now you need u prime or du dx or g prime of x. Now all you have to do, find the derivative of sine of x cubed. The derivative of sine is, all you have to do the derivative of cosine of sine of x cubed. So the derivative of cosine is minus sine with the same argument. And times the derivative of the function of function of the argument of cosine sine x cubed. So what is the derivative of sine of x cubed? Cosine of x cubed. If it was x, would be done. It's not. 3x squared. We rewrite this by putting this one in front. We also have a negative sign, so minus 30x squared. We put this one in front, so minus this one, and this one, minus 30x squared. Cosine of x cubed, cosine to the power of 9 of sine x cubed, and sine of sine of x cubed. We have accounted for the negative sign. This is as complicated as it gets. I highly recommend you look at this a couple of times to make sure you get this. And if need be, everybody, do this. If need be, write this as cosine of u to the power of 10, where u is sine x cubed. And now do the math, okay? Do the differentiation if that helps, okay? F of x is x to the power of 4 times e to the power of 2x. We need to put a raised dot here to emphasize that we are using the product rule first, f times g. And so we are using this. F prime is 4x cubed times g e to the power of 2x plus g prime e to the power of 2x times 2 times f x to the power of 4. So I'm going to write at top of it so it becomes clear what we are dealing with here. So we have f prime g plus g prime f. And I hope you see that number 2, x cubed and e to the power of 2x is in common. Two is in common, x cubed is in common, e to the power of 2. So if you divide this one by this one, it just gives you number 2. If you divide this one by this one, it just gives you x. So 2 plus x. It's a simple factoring, everybody. We want to differentiate 9x times x minus 1 to the power of 4, and we're going to use the product rule again. I'm going to put a raised dot here. And again, I remind you what I mentioned before. If this number is complicated, that means it's extremely large, or it's a fraction or a decimal, you want to put brackets around this and just keep it as a multiplier. You'll notice that the 9 will become a common factor at the end. So, but at this point, this is your f, this is your g. So let me do that. So this is the f function. This is the g function. We're going to use the product rule. So f prime, that gives us 9 times g. Just write this one, x minus 1 to the power of 4, plus g prime. Let's differentiate this. So 4 sits in front. Same thing, x minus 1 cubed. And then the derivative of x minus 1 happened to be 1. And then finally times f, 9x. And again, I'm going to write at top of it to make sure everybody knows what we are dealing with here. This is f prime. This is g. This is g prime f. Okay. Now notice 9 is common, as it was mentioned in the beginning. X minus 1 is in common. This was exponent. This has exponent 4. This has exponent 3. We use the smaller of the two. So if I divide this guy by this guy, it just gives me x minus 1 to the power of 1, or simply x minus 1. If I divide this one by this one, this goes away. 9 goes away. 4 remains an x, 4x. And as you can see, 4x with x, they add up to 5x. And again, I mentioned 9 will remain as a, common factor. And you could have separated it here. It doesn't really complicate anything because it's just 9, but it's your choice. We want to differentiate this. And again, just to make sure we understand what's going on, I'm going to rewrite it on purpose to make sure we don't make a mistake. This is sine 8x to the second power. So something to the second power uses the extended power rule. So I'm going to write the extended power rule, and I'm going to follow that. So n, or 2, sits in front, times sine 8x to the power of 1. See, this one takes a power of 1. I don't write it. Now, all I need is the derivative of the inside. So g prime of x says, okay, find the derivative of sine of 8x. The derivative of sine is cosine. So cosine of 8x times the derivative of 8x. If it was x, we would be done. It's a function of that. The derivative of 8x is 8. Now we're going to put the 8 in front of 2. 8 and 2, the product is 16, sine 8x, cosine of 8x. Three x times 3 to the power of x. Let's give them a name, f and g. And obviously, let's use the product rule. This gives us 3 times g, 3 to the power of x, plus g, the derivative of 3 to the power of x. Remember what's happening. Any exponential, the answer is itself, 3 to the power of x. Is the base e? No. Times ln 3. So we're done with this, times f times 3x. So I hope everybody's clear. I'm going to write at top of it so be clear as to what we are dealing with here. We have f prime g plus g prime f. And we are done with calculus. But we are going to do algebra to finish the job. Notice this one has exponent 1. And we can add up the exponents. Take a look at this one, everybody. You can add up the exponents 1 and 3. So you get 3 to the power of x plus 1. Also, this one has exponent 1. So this one and this one, they give us 3 to the power of x plus 1. So here's how we are going to write the first one, 3 to the power of x plus 1. And this one, we're going to write 3 to the power of x plus 1. We keep the ln 3 and we keep the x. So what happens next? 3x plus 1 is in common. So if I factor this out, this gives me 1, this gives me this 2. And these 2 ln 3 times x. We write it as x ln 3. Why? Because if I put the x after 3, one may think it's ln of 3x. So this gives us 1, this gives us ln 3 times x, and we rewrite it in this fashion. Okay, everybody? Implicit differentiation. Functions expressed by one variable are defined explicitly in terms of another variable. Example, y equals x squared minus 2x plus 1, or in general, y equals f of x. Some functions are defined implicitly by a relation between x and y, such as x squared plus y squared is 25, or x cubed plus y cubed equals 6xy. In some cases, it is possible to solve such an equation for y, and in some cases, it is not easy or even impossible to do so. In such cases, we can use the method of implicit differentiation. This consists of differentiating both sides of the equation with respect to x, and then solving the resulting equation for y prime or dy dx, everybody. Let's look at a very simple example. We want to differentiate 4x plus 2y equals 10 two different ways, explicitly and implicitly. So explicitly, all you have to do is solve for y. That means move the 4x. Divide both sides by 2. And clearly y prime is negative 2. Done. But how would you do it implicitly? 4x, the derivative is 4. 2y, the derivative is y prime or dy dx. On purpose, I want to write dy dx. It's the same thing as y prime. The importance of this is that it's telling the reader what is the independent variable. So again, the derivative of y, you can say either y prime or dy dx. Therefore, you move the 4 to the right, and dy dx, just as before, it's negative 2, everybody. And they are identical. We can do it explicitly or implicitly. In some cases, we can solve for y implicitly and therefore explicitly, and therefore we do implicit differentiation. Use implicit differentiation to find dy dx, where 2x plus y to the power of 4 is x minus 2y. And I want to remind you of the extended power rule. The derivative of g of x to the power of n is n g of x to the power of n minus 1 times g prime of x. And remember, g of x is like y, so d dx of y to the power of n, according to this, is n y to the power of n minus 1 times y prime, or dy dx. So we are going to differentiate both sides implicitly. So we start with 4 times 2x plus y cubed. 4 sits in front, the same thing, the power of 3. Then we need the derivative of the parentheses. This gives us 2, this gives us either y prime or dy dx. And I'm going to write y prime. Normally it's easier to deal with that, but at the end I'm going to write dy dx. Again, the advantage of this is that it's telling us the independent variable is x. So that's done as far as the left side. Right side, x gives us 1, minus 2, y gives us y prime. And believe it or not, this is the end of the story as far as calculus is concerned. And now we are going to use our algebraic techniques to finish the job, which means we are solving for y prime. All right, there are various ways of solving it. So if I distribute the 2, this becomes 8. And then, in other words, multiply this whole thing by 2. This becomes 8. And this whole thing by y prime, you get the same thing times y prime. Why am I writing it in this format? Because I'm solving for y prime, so I'm going to move things around in the following manner. I'm going to move this to the right. And I'm going to move this to the left. The reason why I want to solve for y prime, anything involving y prime comes together. This is elementary algebra, everybody. On the left side, I want to isolate the y prime. That means I'm going to factor the y prime. Now, I'm not interested in 4, 2, because if I want to factor it, I really have to take the 2 out, but it doesn't make any difference. Ultimately, if you have to, you can cancel the 2. But for now, I'm interested in y prime. So from the first piece, I get 4 times 2x plus y cubed. From the second piece, I get 2. So take a look at the left side. The right side, we don't touch it. The left side, we factor the y prime out. And so all you have to do, divide the right side by the brackets. So y prime, or dy dx, is the right side divided by the brackets. So 1 minus 8 times 2x plus y quantity cube over 4 times 2x plus y quantity cube plus 2. So this becomes the denominator. If there happen to be a common factor of 2 in the numerator also, then you have to take the 2 out from the bottom and cancel it from the top and the bottom. If that doesn't exist, you don't have to worry about it. Use implicit differentiation to find dy dx. Sine y plus 2x cubed y squared equals 6. First and foremost, we are concerned with sine y, and I'm going to say sine. We know the derivative is cosine. So cosine y, and then y prime, or dy dx. Then I'm going to put a raised dot in between. So I'm going to use the product rule, everybody. We are going to use the product rule. Two x cubed gives us 6x squared times y squared. So 6x squared times y squared plus y squared gives us 2y dy dx, 2y dy dx times 2x cubed. So I'm going to write this f times g, and I'm going to write this as f prime g plus g prime f. So it's clear as to what we are dealing with. Now, first, I want to combine. So I'm going to write this one. I'm going to write this one. I'm going to combine these two into 4x cubed y. And since I want to solve for dy dx, I'm going to move this and make it negative on the right side. And on the left side, I factor the dy dx out of what remains. So from this one, I get cosine y. From this one, I get 4x cubed y. So all you have to do, divide by the parentheses, and that's dy dx of y prime minus 6x squared y squared over cosine y plus 4x cubed y. Implicit differentiation, everybody. Find an equation of a tangent line for the function x e to the power of y plus y e to the power of x equals 1 at 0, comma 1. We need two things to find an equation of any line. We need a pair x comma y is given, and we need this slope. Therefore, we are going to differentiate the function, and we are going to differentiate it. Implicitly, I'm going to put a raised dot between x and e to the power of y, as well as y and e to the power of x. So it becomes clear that we are dealing with the product rule, everybody. So x, so let me write for this one. Let me write f times, just look at the first piece, okay? Nothing else. So f prime is 1 times g, which is e to the power of y, plus g prime. What is the derivative of e to the power of y? Any exponential, the answer is itself. But remember, if the exponent is x, we are done. But the exponent is y, some sort of a function of x, y or g of x. So we need g prime of x or y prime or dy dx. Times f, which is x by the product rule. So right here, I'm going to write f prime g plus g prime f. Now, the next one, I'm going to call it the same thing, but with a different color. So this is the f function. This is the g function. And we are going to use, again, the product rule. So y, the derivative is y prime or dy dx times e to the power of x. So f prime g is e to the power of x times e to the power of x, plus g prime f. What is the derivative of e to the power of x? It's itself, plus e to the power of x times y. And of course, the right side, everybody, is a number. The right side is a number. The answer is 0. We don't have to worry about it. So let me write this with that color at top of it. So we are dealing with f prime g here plus g prime f here. Now what do? We are solving for y prime or dy dx. By the way, there are two ways to do that. One is just if you plug in x equals 0, y equals 1, by the time you finish the job, you get to the answer for y prime, and that's fine. However, I think it's a good practice for a calculus student to solve for y prime and then plug in. So that's what we are going to do. To do so, anything involving y prime remains. So let me erase this. These two pieces involve y prime, and these two pieces don't have them. So this goes to the right, becomes minus e to the power of y. This goes to the right. So this moves, becomes negative. This moves, becomes minus e to the power of x, y. And so we can write it by taking the negative out. Now, what you see in a red box, we can take the y prime out because we are interested in solving y prime. When I take the y prime out, this will give me e to the power of y times x, or x times e to the power of y makes no difference. And this gives me e to the power of x. So take a look at this one. And the two pieces that they moved to the right, both of them have a negative sign. So all you have to do, divide both sides by the parentheses, by this. So divide both sides by this. So the left side will lose that, and the right side becomes minus e to the power of y plus e to the power of x times y divided by e to the power of y times x plus e to the power of x. So I hope you see that y prime is the right side. We have the negative sign is not going anywhere over this one. And now we are going to evaluate it at this pair, meaning replace, and this is one way to write that, y prime such that we use this pair, x is 0, y is 1. So let's replace anywhere you see x with 0, anywhere you see y with 1, and evaluate it. So we don't lose the negative sign. We get minus e to the power of 1 plus e to the power of 0 times 1 over e to the power of 1 times 0 plus e to the power of 0. So clearly, this one first goes to 0, so we don't have to worry about that. As you know, e to the power of 0 is 1, so this is e, and this is 1. So e plus 1 in the numerator, 1 in the denominator, and don't forget the negative sign. We get minus e minus 1. Now, I'm going to use y equals mx plus b because the y-intercept is given, and therefore this is b. And I'm going to write it in this format, y equals m, which is minus e minus 1 times x plus 1. And you can leave it like that. This is an exact method, everybody. This is an exact value. Needless to say, this is a number. Remember, EE is like 2.718. So they add up to negative 3.71828, and it continues indefinitely.